Hi everyone. In this section, we'll cover GMT concepts for seismology using material developed by Dongjong Tian. GMT provides 4 different modules for seismology, shown in this figure here. We have Mecha to plot a planar view of focal mechanisms, Coupe to plot a cross-section view of focal mechanisms, Polar to plot polarities on the lower hemisphere of the focal sphere, and SAC to plot seismograms in SAC format. And in this section, we'll focus on Mecha and Coupe. For more information on exactly what focal mechanisms are, we recommend this IRIS video, What Are Those Beach Balls? We won't be covering the fundamental concepts in detail during this section of the course. We'll just be focusing on how to use GMT to visualize those focal mechanisms for beach balls. We also would refer you to the Mecha documentation in the GMT docs, the Coupe documentation, and the global CMT project, where we've gotten some of the example data for this module. So just briefly, focal mechanism describes the movement of the fault that generates seismic waves. So from focal mechanism solution, we can know the orientation of the fault plane and the slip direction. And a beach ball is a graphic representation of the focal mechanisms. So in this figure, we show the 3 simple focal mechanism solutions for a normal fault, a reverse fault, and a strike slip fault. And each of these can be created using GMT. So let's get into how to do that. We'll use this set of sample data here. So each row contains information about a single earthquake. The first row is for a strike slip fault. Second is for reverse, and third is for normal. And we have 8 different columns. The first column is the longitude. Second column is the latitude. The third column is the earthquake depth. And then we have 3 different parameters characterizing the earthquake. So we have strike, dip, and rake. Finally, we have the magnitude and then a description of the event. So the event title describing what type of earthquake occurred. So to get started, we will copy these data over to a new data file that we'll be working from using GMT. So we'll call this mecha.dat and create this data file. We'll also need a script for running the GMT commands. So we'll call this beachball.sh to indicate that it's a shell script. Now let's get started with creating our GMT script. So we'll, as usual, start with GMT begin, and we'll call our figure beach ball, and we'll make a PNG figure. Then, as usual, we do GMT end to conclude the GMT modern mode. You can use show here to automatically open the figure that was created. We'll leave that off for this example. And in this example, to create these beach balls, we'll use GMT Mecha. The first thing we need to do is pass in our data file. So we'll do mecha.dat to pass in those data. And then you can look at the specification for the GMT Mecha module in a couple different ways. First, you could do GMT docs Mecha, which would open up your browser to see the HTML representation of the documentation. Or you can use GMT Mecha minus question mark, which shows the docs directly on your terminal. So if we scroll up, we can see the different optional arguments, and then we see the required arguments. So here we can see that minus S is a required argument, and it specifies the format convention for your data. So here we tell GMT what types of earthquake parameters are being provided. The first one is A, so this is the focal mechanism for Ecke and Richard convention. We have longitude, latitude, depth, strike, dip, rake, magnitude, optionally new X, new Y, and event title. So that is what we have in our data file. So we'll use minus SA to specify that is our convention. If you had your data in a different format, you could specify one of these other ones. For example, minus SC for a focal mechanism that's stored in the global CMT convention. The second part of this minus S option that we'll provide is the scale. So that for this, we'll use 1c for centimeter as the scale. So now we have our most basic format for our GMT scripts that plots focal mechanisms. So let's run this with bash beachball.sh. And we have a just small typo, so mecha.dat. So we'll run this, and now it completed without error. So we can go back, open to the side this to see the output from our script. So we can see that the focal mechanisms were indeed plotted, but they're very truncated. So the center is at the earthquake location, but the edges of the beach balls are cropped from our figure. So to fix this, we can add a base map. And this has the added benefit of showing the geographic context for these earthquakes. So GMT base map, we'll use our common options -J for the projection. So we'll make a 10 centimeter wide Mercator plot, -B for the frame. So we'll do automatic annotation. And then we'll use -R to set the region. And so we can go back to our data file to show, to take a look at the range of values, which are generally around 115 longitude and centered around 33 latitude. So for this, let's make a go from 110 to 120 longitude and from 30 to 35 latitude. And we can run this again. Now we have a nice map that shows the geographic context and the full focal mechanisms. So you can see we have a beach ball for a strike slip, reverse, and normal fault. And you can also see that by default, GMT colors the compressional area in black and the extensional area in white. And that those event labels are plotted by default on top of the focal mechanism or the beach ball. So you could also might notice that these different beach balls are different sizes. So this 1 centimeter is the reference size for a magnitude 5 earthquake. So earthquakes that are smaller than that will be plotted smaller than 1 centimeter, and conversely, larger earthquakes are scaled for larger sizes. If we instead want all of these to be plotted in the same size, we can append the +M modifier to this -S option for mecha. So now if we rerun that script, we can see that all three beach balls are the same size. The other modifiers for the -S option mostly control the appearance of the labels for these different beach balls. So as one example, +F controls the font size and color. So for example, if we do +F 0p, specifies a 0-point font size, so in fact, the labels aren't plotted. Or we could make it larger using something like a 24-point font size. We can also do an angle of the beach ball labels using +A. So for example, 10-degree angle. And we can also control the justification using +J. This is used oftentimes throughout modules that control different aspects of text positioning. So we can use top left to justify it towards the top left. And then we could do offset, so +O to specify a 0.5 C X and Y offset for these labels. We'll return to our original specification showing the beach balls plotted proportionally to their size with the default labels for each of these. So now you've seen how to create using mecha beach balls showing representation of these different focal mechanisms. Using the mecha module of GMT, you've seen how to pass in your data file and how to specify the convention for that data file using the -S option. We can also, once again, use the different modifiers to control the label appearance for these different beach balls, as well as the scaling for the beach ball size. So that concludes this segment of the seismology section of the short course. In the next section, we'll show how to control a few different more aspects of these beach balls for visualizing focal mechanisms. In this section of the seismology portion of the short course, we'll show how to offset the beach balls from the earthquake location, as well as color the compressional and extensional portions of the focal mechanisms. So let's start by showing how to offset the locations of the different focal mechanisms. So to do that, we add two columns to the input data set. So here I've added an offset y x and an offset y location column. The offset x column shows the longitude that the focal mechanism should be plotted at. So in this example, we have our original longitude is 112, but the focal mechanism should be visualized as the beach ball at 113, similarly 33 rather than 32 latitude. We can specify that the focal mechanism should not be offset using 0, 0 as the value for both of these columns. So if we go back to our script and run it, we see at first that there's actually no difference between our original figure and this figure after having added those two columns. So in fact, we need to add the -a option for Mecha to specify that those columns should be interpreted as an offset location for the plotting. So now, since we had values for that, for the strike slip fault earthquake, we see that focal mechanism is indeed offset. The others are not because we had 0, 0 as those values. So we can specify different locations for all three by adding in longitudes and latitudes in those offset x and offset y columns. So now if we run them, each of these three different focal mechanisms are offset from the earthquake location. If we want to make the connecting point or the connecting vector between the earthquake location and the focal mechanisms a little more apparent, we can use a +p modifier. So for example, +p specifying a 1-point thick pen and that's colored red to make that a little bit more visually striking. We can also color or plot a circle at the original earthquake location using the +s modifier. So here we make a 0.1 centimeter in diameter circle at that original location. So now we have shown how to offset the beach balls from the earthquake location, which can be really useful during instances in which you have a lot of earthquakes in a very close proximity to each other, such that the actual focal mechanisms would probably overlap if they were not offset. If we want to change the color of the compressional and extensional parts of the focal mechanisms from the default black and white, we can do that using the -e and -g modifiers, or options, excuse me. So -e controls the color of the extensional zone. So we can say, for example, light red, and -g is for the compressional area. So we'll make this dark blue. So far we've seen how to offset these focal mechanisms from the earthquake location and color the compressional and extensional areas with specific colors. If we go back to our original example, we can see that using these different options, we can see the location of the earthquake, you can see the orientation, the dip of the earthquake, and you can also see the earthquake's relative intensity, or because the size is proportional to the magnitude. What is difficult to see that is in our original data is the depth. And so to do that, we can color the compressional area of the focal mechanism based on the depth of the earthquake. So in this example, we have the depth is our third column. So the depth ranges from about 15 to 45. So we can make the color of the compressional area scale with this earthquake depth. And we do that using -c. And we also need to make a color map. So we do that using GMT make CPT. We specify -c what color palette we want to use. Here we'll use the Batlow color palette. And we need to specify the minimum and maximum range for this color palette using -t. So we saw what that range of depth is, so we'll make it go from 0 to 50. So now if we run this again, we have the compressional area plotted proportional to the depth of the earthquake. We don't have any context for what these colors mean, so we can fix that by adding a color bar. So GMT color bar. We'll create some annotations on that, a label, call it depth in kilometers, and we'll justify this in the middle right. So now you can see that the normal fault is the deepest, strike slip is shallower, and the reverse fault earthquake is shallower still, corresponding to these depths in our input data set. So in this section of the seismology portion of the short course, you've seen how to plot different earthquakes using the MECA module. You've seen how to specify the convention, how to specify the color, and how to map the depth onto the color of the compressional segment of the beach ball. And so that concludes the MECA portion. In the next segment, we'll cover how to plot cross sections of focal mechanisms using the COOP module. In this section, we'll show how to plot cross sections of focal mechanisms using GMT's COOP module. So let's start by creating a new script called crosssection.sh. In this, we'll set up another GMT modern mode session using GMT begin. We'll call this cross section, and we'll make it a PNG output, and we'll use GMT end to terminate the modern mode. For creating these cross sections of the beach balls, we'll use GMT COOP. And the input data format for COOP is the same as for MECA. So we can pass in meca.dat. Similarly to MECA, we can use the -s option to set the convention. So we'll do -sa 1 centimeter again. If we go ahead and run this, we get an error. So we need to specify the -a option. Once again, it's possible to look at the documentation by typing GMT docs COOP, which will bring up the HTML representation, which is generally easiest to read, but we can also use the command line documentation to look at what is needed for this -a option. So this is one of the most unique aspects of COOP, and it specifies exactly how GMT should plot this cross-section. So we have -a, and we can specify, for example, that we want to show the, or put in the geographic start and end points using -sa little a. And we can append the longitude, the latitude for the starting point, and the longitude and latitude for this ending point. So here we'll make a cross-section across the longitudinal range of this original planar plot. So let's specify the starting lat as 110, 30, let's say 33, and the end as 120, 33. If we run this again, we will once again get an error. So we need to either specify the -r option or -a plus r. And so this -a currently specifies the x range of the plot, but it doesn't have any information about the y range. So we can have GMT automatically determine the y range using +r. So now if we open up this cross-section, we see the beach balls plotted, but we don't really have any information about or context for their location. So let's add a bit more context using the common projection and frame parameters. So the projections, this is a cross section, will just be linear, so -jx. And so with this, we can specify the width as 15 centimeters and the height as 5 centimeters. And we can specify the frame information using minus B. So we'll do automatic X labels and automatic Y labels. So now we can see a little bit more context for these focal mechanisms, but it would be even more helpful if we added X and Y labels. So let's do that. We'll add plus L for a label on the X-axis called distance, kilometers. And similarly for the Y-axis, we'll have plus L depth, again in kilometers. So now we can have a little bit more context, but we'll want the depth increasing downward on the Y axis, and we can do that by specifying negative 5c in the projection parameter. So now we have depth increasing. You can see that this plot is already showing a lot of context, but probably we'll want to specify that the y-axis will start at 0, and maybe we want to control exactly the maximum depth along the y-axis. So rather than using the plus r modifier for automatic characterization of that depth, we can instead directly specify minus r. So now we'll have the, similarly to before the minimum x, we'll still go from 0 to 1000, so a little bit further along, and then on y we'll go from 0 to 60. So now we have it nicely increasing from a minimum depth of 0. Similarly to with Mecha, we can control the color of the compressional and extensional parts using minus E and minus G. So we'll control the extensional section with minus E. We'll do light blue, and we'll specify the compressional area as red. So now, in addition to plotting planar views of focal mechanisms using Mecha, you can you know how to plot cross sections of focal mechanisms using Q. In the GitHub repository for the GMT for Geodesy short course, there is a exercise that I would encourage you to explore in order to try to understand these concepts a bit better. So in that exercise, you can download data from the global CMT catalog and plot it using both Mecha and Q. So thank you for watching this section of the short course. And again, please reach out either through the Slack workspace if you're a participant in the live portion of the course, through our office hours, or more generally through the GMT forum.